In this video, we're going to be talking about accelerating the development of a control valve using the predictive analysis capabilities of Physics AI. CAE simulations are a game changer in the engineering industry, allowing us to test designs and variants and assess their effectiveness without the need for expensive and material heavy physical testing. However, these CAE simulations have some flaws, namely the fact that they require an immense amount of computing power and are often tedious and time consuming to actually run. This is where Physics AI comes in. Let's look at the problem at hand. Product design and development of a control valve would require optimizing the valve geometry using various parameters, namely the stem travel, CV, and valve diameter. What makes this especially tedious is the fact that multiple stem positions must be tested for each valve variant, and the fact that you have to run an individual simulation for each specific position makes it time consuming and resource heavy. The goal is to use Physics AI with the existing simulation results to generate predictive results for any further variants of the control valve. This helps us to enhance the optimization efficiency and reduce the computational cost and simulation time required for testing. So, what exactly is Physics AI? Simply put, it is a geometric deep learning engine which runs on the basis of a neural network. It works through thousands of processing layers and allows us to generate full fledged simulations based on existing simulation data. It can predict both implicit and explicit variables, and its code free nature makes it an accessible and easy to use solution for most industries. Now, let's talk about the process to actually create a model, train it, and then use it to make predictions in Physics AI. The first thing you'll want to do is open up Hypermesh and then navigate to the Physics AI ribbon at the top of the screen. From there, the first thing that you will want to do is create a new project. So just give it a name, let's just say demo proj, and pick a location for it. Just here, like that, and you should be set. The next thing that you'll want to do is create a data set. Again, just click on the plus at the top of the screen, and that should take you to this create dataset page. Again, I'm going to name it demo dataset, and then again select a location. The datasets that you create are the foundation of Physics AI. So we have here simulation results that were obtained for a valve of diameter 24 and CV 7.5 and CV 12. And we're going to use these as a training and testing data for the Physics AI model that we're going to train. So we just select these, select all of them, and then just move them over to the other side. And these are the files that will be requested and loaded. I'm not going to include the 15mm for the CV 7.5, and we will see why later. Essentially, we're going to use a geometry model for this specific value and then use that to showcase Physics AI's predictive capabilities. So just going to exclude that. Enable train test splits, so we have a dataset that can be used for training and a dataset that can be used for testing. And we're going to extract simulation properties because we can, and then we will see what happens next. So as we can see here, the dataset has been created, and we can now take a look at the values, or like the files that are a part of the dataset. Now let's get to the interesting part of Physics AI, the model training itself. So when we head into the model training, this is what we will see, right? There's no models in here just yet, but all we can do is either click on the plus over here or just click on the create model tab right here. And now we have this entire set of things to look at. So let's break this down bit by bit. Firstly, we have the model name, of course, and on the left side are the inputs, the right side is the outputs. So Physics AI decides what it should take in as an input and what it should check the parameters of based on your inputs over here. And the outputs are what you want physics AI to predict. So in my case, I would like physics AI to predict pressure based on the inputs of the CAE coordinates. Methods simply refers to the architecture that physics AI uses for the training. So we have GCNS, which as we can see is the graph context neural simulator, and the TNS, which is the transformer neural simulator. Both of these fulfill the same function at the end of the day, is just which architecture helps suit your use case best. Typically, the transformer architecture is faster with GPU based learning and is a lot more resistant to noise when it comes to training. However, you don't necessarily need to train a model from scratch either. A key component of his AI is the feature known as transfer learning. If we select this, we can choose a pre-trained model. Let's say we go into here, and I actually do have a model that I have trained here already. And if we select this, then physics AI will use the previous training from this model and apply it to the data set that is currently active. In other words, you can take a more generalized data set that's already been trained before and then further fine tune it to your specific use case. However, since training a data set will take time, what we can do instead is simply, so just cancel out this. We still have to recognize that training a model takes time, and so what we are going to do instead is we're going to just simply import a model. Now this helps us save time on the training, and we can use a model that has been trained before for multiple use cases and on multiple machines. So what we can do is name this type of model as well, and we're going to go back to that model that we had just mentioned earlier for transfer learning, and we're just going to import it in its current form. So we just bring it in, and let's just set it as an active model as well. This is basically the model that we will be using to run the predictions on files that we import. That's what an active model does. So we just import it, and now it's active pretty much. Now let's move on to the testing phase. So we have our model, we have our testing data set, and we can run a test. So with the testing done, we can just see the results here. So let's get on to the interesting part of physics AI, the actual prediction itself. So what we can do is, I'll just head into downloads here, and we have this file that was sent for prediction. We just drag it in, import it as a new model, make sure that the values are MKS because that is what we have trained the model on, and now we just wait for it to be imported pretty much. And there's our model for the control valve, and what we're now going to do is simply make sure this model is active, which it is, and then just click predict. This will typically take a minute or two, but it's still far quicker than running 3-hour simulations or multiple hour simulations, and this saving is especially great when it comes to the time saved and the computational cost. Now let's take a look at the final predictions that were obtained. We ran predictions for 3 separate models. The first one was for a plug of CV12 and travel of 4 millimeters. This is actually not included as part of the original dataset, so we decided to use it as part of one of the predictions. Upon closer look, we can see that it's captured the trend across the plug surprisingly well. Normally, we find the accuracy and the confidence of physics has in a prediction on the basis of the similarity score. However, despite the fact that it does not seem to be ideal, it's nevertheless captured the pressure difference across the valve in a rather convincing manner. Next, we move on to the CV 7.5 and 15 mm travel plug. Now, Here we notice that it's captured the trend across the pipe of the valves relatively well. However, it's not done quite as well when it comes to capturing the pressure difference across the plug, since the fluid would hit the plug before it actually moves into the further part of the valve. Again, the predictions similarity score is not the highest, so we could decipher that there's possibly some discrepancy that is part of the data, and trying to figure out and work towards fixing these discrepancies is also a part of the process. Now we have a CV5 and travel 15 millimeter example, and again it's predicted across the valve but not quite as well on the plug. Further testing will need to be done to verify why this is the case and what discrepancies exist in the training slash prediction data, and from there the model can be further fine tuned and refined in such a way that it's able to predict even the plug with high accuracy. Overall, much like the CAE simulations were back when they were first introduced, Physics AI itself has the potential to be a game changer in the industry. The ability to generate multiple predictions with a click of a single button without the need of spending 3 to 4 hours on each individual simulation is a massive amount of time and computational cost saved. The potentials for this are endless. The only limit, the data we provide to it, and our own imaginations.